This conference will now be recorded.
So, very good morning, student. Today, we are continuing the discussion on kinetic theory of gases. Here, we have already derived the equation of pressure according to kinetic theory of gas in the last class. If you remember, P is given as 1/3 rho V average square. Okay, so this is what we have found out from kinetic theory of gas. Okay, only this single derivation will help me to find out the kinetic interpretation of temperature. Like I can derive temperature from here. I can get a meaning. I can actually realize the meaning of temperature from this particular formula, 1/3 rho v average square. I can find out all the laws like V proportional to T, P proportional to 1 by V, and then P proportional to T. All those laws we have already discussed. I'll derive those things from this particular expression of pressure which I have got from kinetic theory of gas. And then we'll discuss the Maxwell speed distribution. This is also an important topic, even though we are not going to the detailed derivation of that distribution, but we'll just learn few things which are outcome of the Maxwell distribution, speed distribution curve, okay, or the speed distribution equation. So first of all, let us try to understand or interpret the temperature in terms of kinetic theory. So actually you have already learned from thermodynamics that internal energy is directly proportional to this temperature. For ideal gas, this internal energy is equal to average kinetic energy of the molecules. That's all. Average kinetic energy. For ideal gas there is no potential energy. So only kinetic energy, and that too if we take translational kinetic energy alone, then this one we can write. So see, in the kinetic theory of gas we have got P is equal to 1/3 rho V average square that I had already written few minutes back. Okay, so let us see how we can interpret temperature from this particular equation. First of all, let us consider 1 mole of a gas, an ideal gas obviously, 1 mole of a gas which has pressure P, volume V, and it is at temperature T. This is the equilibrium temperature, and suppose the molecular weight is capital M. Okay, now this is molecular mass, we generally say weight also. So we can get one thing from here. See, we can get the density of the gas from here. How? Molecular mass. divided by the total volume of the gas. Okay, this we can write. Now look, we have, according to kinetic theory of gas, the expression for the pressure which is exerted by the gas. This particular gas, suppose, is exerting a pressure on the walls of the container, and that pressure can be written as P is equal to 1/3 rho V average square. And see, this expression itself, we can replace this rho by writing m by v. M by v, because this is the density of the number of molecules. Okay, and V average square as it is. All right, look, in this is actually volume. So from here we can write P capital V M V average square. In front there will be 1/3. See, this can be written like this also. I hope you agree with me. I have just multiplied 2 and then multiplied half also, so that this will help the equation to be unchanged. So this part is actually called average kinetic energy. Average kinetic energy. This part is called average kinetic energy of a gas, Okay, average kinetic energy. I'm writing in abbreviated form, kinetic energy, and that is actually denoted by E. So if we denote this as E, capital E, so what we get is PV is equal to into E, 2/3 into E. So this we can write. Now from ideal gas equation, sorry. So I hope I can remove this part now. We know from ideal gas equation. What is that ideal gas equation? That is PV is equal to RT. Okay. Now if we write if we replace this PV with RT, so what we can get, actually we can get 3/2 into RT out of here. Okay, from here. So what is this? This is average kinetic energy. This is actually average kinetic energy. Average kinetic energy of gas. So average kinetic energy, see, this R is actually universal gas constant, you know that, and this 3/2 also a constant. So what you can say, average kinetic energy is directly proportional to the temperature. So this is the interpretation. This is the interpretation of temperature in terms of kinetic theory. So what we have got? We have got average kinetic energy of gas, average kinetic energy of a gas. Obviously this I am taking as an ideal gas of 1 mole. What is that? 3 is equal to, sorry, E is equal to 3/2 RT. So this R is universal gas constant, this T is temperature. So we can write from here that E is directly proportional. So this is actually internal energy, sorry, kinetic energy, average kinetic energy. And when we talk about only ideal gas, then the gas does not have any other source of energy, only this average kinetic energy they have. And we can see that average kinetic energy is directly proportional to temperature, which is nothing but, see, it is proving this also, internal energy is directly proportional to temperature. Okay, now if I Now if I know that there are n number of, n is the number of Avogadro number, right? Avogadro number. If this a Avogadro number, if this n is Avogadro's number, then average kinetic energy. Okay, so now if we do one thing, so this is actually for 1 mole. So in 1 mole there are n number of molecules. So I can find out uh, average kinetic energy per molecule. Average kinetic energy per molecule. So that I can write in terms of E bar. So there are n number of molecules in the Avogadro, in the 1 mole. So I can just divide with R, then n and T. So this R by N will give you the Boltzmann's constant. This is 3 by 2 kBT. 3 by 2 kBT. So what does this mean? This means the mean kinetic energy per molecule is proportional to the absolute temperature of the gas. It is independent of the pressure, volume, and nature of the ideal gas. See, whatever may be the ideal gas, whatever may be the pressure and volume, does not matter. You can see that average kinetic energy, average kinetic energy per molecule, average kinetic energy per molecule is 3 by 2 kT. Okay, 3 by 2 kT. That is directly proportional to the absolute temperature. Now I can do certain things from here itself. Let me clean it up. So what we have got? We have got average kinetic energy per molecule. So this we have got as 3 by 2 kBT. Or let me write this. Okay, E is equal to half mv square. That is what we have taken. Average kinetic energy half mv square. Okay, so from here, since this E is 3 by 2 RT. Okay, let me write in the left hand side itself. We have seen that half capital mv square is equal to 3 by 2 RT. See, from here, half goes. So from here, you can find out the average velocity. Average velocity, what is that? What is that? 3 RT by m. Square root of 3 RT by m. So this is actually the average velocity. Average velocity. I'm sorry, this is not average velocity. Just a minute. This is actually called. Okay, this is mean velocity is this square mean, and this is called root mean square velocity, not average. Root mean square, because we have already taken mean square velocity. Now it is taken a root mean square. This is called root mean square velocity, or RMS. Average velocity we know already. This is actually root mean square velocity, RMS. Root mean square means RMS. So we have to go from back side. Square the velocity. Take average. Mean means average. And then square, and then root. Take root. Square, mean, and root. So this is mean. This is meant like RMS. By RMS, this root mean square is meant. Here RMS velocity means it has root mean square velocity. Okay, so root mean square velocity is root over or square root of 3 RT by m. M is the molecular mass. Okay, now we'll go to the derivation part of various law. Now we'll derive various laws. See, from the kinetic theory of gas. Various laws from kinetic theory of gas. First, we'll derive Boyle's law. Okay, Boyle's law from kinetic theory. The kinetic theory of gas sometimes is abbreviated as KTG. Okay, kinetic theory of gas, KTG. So I'll write here in short or in abbreviated form. That's why I'm telling you this. Boyle's law. So this Boyle's law, what is Boyle's law? We know that P is inversely proportional to V. So this is actually Boyle's law. This we have to prove. We have to prove this from kinetic theory of gas, KTG. So in the kinetic theory of gas, we have got only one formula. What is that formula? That is P is equal to 1/3 rho and V average square. So only this formula we have got. From here we have to prove this equation. Okay, this law we have to prove. Anyway, we know if I have taken a gas having pressure P, volume B, temperature T, and molecular mass is m, then I can write this as 1/3 rho, as we have written m by v. We can just write here also, and then we can write v average square, right? So look here, I can write this as PV is equal to 1/3 m and v average square. Okay, so from here I should have got PV is equal to some constant, so that I can write P direct inversely proportional to V. That we can write from here. If somehow the right hand side of this equation is proved to be constant, then we can prove this P versus 1 by V. This we can prove. But how can we say that 1/3 m v not v average square is a constant? We can say it is a constant because that this is actually half m v square is the total energy, right? Kinetic energy, half m v average square, kinetic energy. So this kinetic energy is constant for a particular temperature, if you remember, because we know the kinetic energy per molecule depends only on the absolute temperature. So in case of Boyle's law, what is the statement? At constant temperature, volume of a particular gas, volume of an ideal gas is inversely proportional to, pressure of an ideal gas is inversely proportional to the volume. Okay, so in this, temperature is kept constant in Boyle's law. If the temperature is constant, so this term, this average kinetic energy term, this also will be a constant, right? If T is constant, in the statement of the Boyle's law, we say at constant temperature, right? It happens in the constant temperature. So, at constant temperature, this part will be constant at any constant temperature. Any constant temperature. Okay, So we can write PV is equal to constant, because in the Boyle flow we know temperature remains constant. So PV is equal to constant, and here we can write, if this is a constant, so P can be written as 1 over V. One over V, P is directly proportional to 1 over V. So this is actually derived. So the key point over here is that we have used the fact that the average kinetic energy of a gas molecule is directly proportional to the absolute temperature. Okay, that is the fact we have used here. So we have written 1/3 m averages V average square to be a constant, and that constant will be equal to P per, P proportional to 1 by P. Okay, anyway, let us go to the next one. So next we are going to derive Charles law. So how to derive Charles law? Charles law. What is Charles law? Charles law actually says this. Okay. Anyway, we will. So this we are deriving Charles law. We are deriving from KTZ. From KTZ. Kinetic theory of gas. So we know P is equal to 1/3 rho V square V average square. So similar thing I'll write over here also, 1/3 capital M by V rho this. Okay. Now what we can do is, because we are going to do this, so in place of P I'll just replace this. I'll just take this V over here and I'll write 1/3 M by P. So this M by P. Okay. So in the Charles law, what is the statement? P is constant, constant in Charles law, right? Charles law, sorry, Charles law. If pressure is constant, then this term, if you look, this will be a constant term. So this M by, okay, anyway, so V is then directly proportional to, this volume is directly proportional to V0 square, V average square. And average velocity, average velocity or average kinetic energy in turn, the square, obviously it depends on temperature. So we can say that V is directly proportional to temperature. Okay. So we'll see P in the Charles statement, pressure is constant, then only this volume will be proportional to the kinetic energy or the velocity, average velocity square, and this square is actually directly proportional to this. V square is the, like, V, this is actually the velocity, is directly proportional to the temperature. Okay. So this proves that V is directly proportional to T. This is Charles law. Now I have got another law, that is Gay-Lussac's law. That also will derive here. Sorry, this Lussac, Galussa. So Gay-Lussac's law this Gay-Lussac's law, what is the statement? P is directly proportional to temperature. P is directly proportional to temperature. This is what we have to prove. So similar thing. P is equal to 1/3 rho v square average. So this can be written again 1/3 rho means m by v. So this is 1/3 rho v average square can be written as m by v. So from here you can see that in this statement volume remains constant. So P is directly proportional to V average square, and that in turn will be directly proportional to the temperature, because the average kinetic energy of gas is directly proportional to the absolute temperature. Okay, so now we'll learn about Maxwell's speed distribution. So what is actually this speed distribution? You know, I have a gas, like I have a container of gas. I have a container of gas. I have gas molecules scattered or distributed all over this particular volume like this. Okay. But gas molecules are actually mobile. That's what kinetic theory of gas we are learning. That gas molecules are not at rest. They are actually mobile. So if the gas molecules are mobile, then see in this region there are many molecules. At least you can think of Avogadro number of the order of this. So these many molecules are there within this particular like this particular enclosure. So all the gas molecules are mobile. That means what? They will collide each other. When they collide each other, they will exchange their kinetic like energy. Exchange will happen from there. So when there is a collision between different molecules, obviously it happens always. So that's why there will be a distribution of velocities. Okay, there will be a distribution of velocities or wide range of velocities of the molecules. A huge range of velocities. Huge range of velocities means some will be having. I'm just giving a distribution. Suppose 10 meter per second, then 20 meter per second, 30 meter per second. Like that, if some molecules are having velocity between 10 and 20, then they are also counted. Like that, if we count the number of gas molecules within the container is very large, and there will be a lot of collisions and there will be a lot of change, like there will be a wide range of distribution of velocities. And Maxwell, James Clerk Maxwell, he was the first person to derive a mathematical formula for this most probable velocity, or this. Okay, so Maxwell's distribution, I'll just write down the mathematics because the derivation part is not included over here. So Maxwell's speed distribution, according to Maxwell, the number of molecules remain within the velocity v and v plus dv. So that is given by 4 pi n a cube e to the power minus b v square. Actually, this is the velocity distribution, and this can be written in short as nv dv, or sometimes people write fv and dv. Sometimes people write fv dv. What does this mean? This means this is the number of atoms, number of at molecules, number of molecules with number of molecules with velocities lambda and lambda prime. I'm sorry, this is okay, this I'll this is v, not lambda. I should write in terms of velocities. So so this is not the velocity. This is actually number of molecules with velocities v and v plus dv within this range. The molecules which have velocity within this range is called actually nv. Okay. Now this a and b, these are actually some constants. a is given by m by 2 pi kbt, 2 pi kbt, m by 2 pi kbt, and b means m by 2 kt, 2 kbt, m sorry m by 2 kbt. Okay, so these are the values. So you can remember this with velocity how it changes. So the most important thing is this curve. This is the distribution of the speeds. Okay, so what we can say, so look, this is the number of molecules plotted in the y-axis, so which I can write as nv. Now the speed, this nv, like see dnv was 4 pi e to the power naq, sorry, 4 pi aq, and other things are e to the power so this is, yes, in e to the power minus bp square. There will be n over here. Okay, so this is the number, total number having velocity between v and v plus dv. Now from here actually we can derive various velocities: most probable velocity, most probable velocity, then root mean square, RMS velocity, then average velocity, and most probable velocity itself, so which is written as Vp, and average velocity AV. Okay, so these are the things we will see in the next class, how we can derive this RMS and this average, and this is the most probable velocity or the speed. One thing I can just convey you that there are certain important features of this distribution, speed distribution curve. This is called Maxwell speed distribution curve. So in this curve you can see it is not very symmetric about this line. Most probable velocity is this line. So you can look, left hand side has less area than right hand side. Why is it so? Because electrons can have velocity, lowest velocity 0, and below 0 there is no velocity, but upper limit is there is no bound. Electron number of electrons which are having the okay, so which are the velocity which with which most of the molecules are moving is called most probable velocity. Okay, so the important feature is that it is not symmetric about the most probable velocity. Right hand side is larger area, having larger area than the left hand side of the most probable velocity speed curve. Okay, so it is because the right hand side there is no limit for the higher velocity, but in the lower side you have smaller area. Okay, then look this curve at any temperature, the peak will give you the most probable velocity. Now if the temperature is increased, then see the curve is becoming wider, but at low temperature it was sharper. So what is the reason for this? In this curve, area under the curve will be always constant. Area under curve will be unchanged. Under the curve it remains unchanged at any temperature. Okay, remains unchanged at any temperature. That's why when you increase the temperature, look, the highest or the maximum velocity is actually the number is actually, see, you can see this peak temperature, peak value is shifting towards right hand side. At the same time it is getting flatter. So to keep the area unchanged under this curve, the probability with the velocity, this broadening of this peak happens. Okay, so with this we will stop it here for today. Next day we'll take up most probable this Maxwell speed distribution, that mathematical form, and we'll try to derive RMS velocity, most probable velocity MP, and average velocity V average. Okay, these three things, and we'll try to see what are the interrelation, what is the ratio, like this is to this is to this. Okay, those things we'll see in the next class. Okay, we'll stop it here for today. So next class will be on Saturday morning, and also in the Sunday also I'll be able to take another class. Okay, so bye for today.